Okay, today is our second and probably last day of homogeneous dynamics and projection theory. Let's remember where we are, and then we're going to try to use the things we learned about last time to say something about dynamics. Okay, so we'll have a Lie group G, which so far is SL2R, and we have a discrete subgroup, which so far has been SL2Z. And we're interested in G mod gamma. We have a metric, M, which is a right invariant metric on G. And then it leads to a metric that I'll also call M on G mod gamma. OK, so now G also has a left action on G mod gamma. And this left action does not preserve the metric, because the metric is not left invariant. So this left action distorts the metric. And we started to study that last time, and it's going to continue to be crucial, how it distorts the metric. But it preserves the volume. OK. OK, now inside of this group, we have the unitary group, the unipotent group. And let's say UT is 1, 1T. And our goal is to understand how the unipotent orbits in G mod gamma look. So we're going to study U dot x in G mod gamma. So x is in G mod gamma. And there's an old theorem of Headland from the 30s, which is the kind of thing about this orbit that we're interested in, that U dot x is either periodic or dense. We won't exactly prove that, but we'll prove some things that are a little bit related. OK. Now, the unipotent group is special. And the one way of getting our hands on something special about it is to see how it relates to diagonal matrices. So let's say this A sub r is that matrix, that diagonal matrix in SL2R. And then a cute observation is that A sub r ut A sub r inverse is u e to the 2r t. It's just a computation with matrices. I've done it a couple times, and I start to sort of, anyway, doing it in front of you I think is not very useful. But if you are interested in this, if you do it yourself, it starts to make sense. OK. So now let's say that u0t of x, that means the set of ut of x, t is in 0t. So if capital T is large, this is a big piece of an orbit. And that's more or less what we'd like to study. What is the shape of a big piece of the orbit? And this observation tells us that u0t of x is ar u01 ar inverse of x. OK. And this is helpful because this u01 is much less intimidating than u0t. So this here is just a little piece of the orbit. And so to understand a big orbit, we have to understand how this A sub r acts on a little orbit. OK. And another simple observation is that AR is like a little r to the j. So if big R is big J times little r, then we have this. Oh, and in this equation, by the way, e to the 2 big R is t. OK, so this AR, we can think of it as a little r applied many times. OK, so therefore, it makes sense that we could just try to understand how a little r acts on unipotent orbits. OK. So we made a picture of this at the end of class last time with models and props and everything. And this picture is the main tool that we're going to think about for homogeneous dynamics. So I'm going to draw this picture again, and then we're going to talk about why it is the way we drew it. OK. So over here, a shape that I'll draw as being kind of a cylinder. And this is a fundamental domain. So this is either the whole fundamental domain or maybe a tube in F. So F is sitting in the group G, and it's a fundamental domain for G mod gap. OK. And so this length scale is 1, and this length scale is also 1, or we could also make it smaller if we'd like to have a thinner tube. All right. And now inside of this tube are a bunch of pieces of unipotent orbit that I'll draw like this. Okay, so each of those is a piece of unipotent orbit. Here is t equals 0, and here is t equals 1. OK. And now we're going to understand what is going to happen to this picture when we apply a sub r. So what we're going to apply, I guess strictly speaking, we're going to apply it on the left. We're going to multiply by a sub r on the left. OK. So what's going to happen? So first of all, the unipotent orbits are going to stretch that way. And then, second of all, OK, so if you just think about what happens to the cylinder, there's going to be a direction where it stretches, there's going to be a direction that compresses, and there's going to be a direction that stays the same. That will be true at every point. But what's important is that the direction that compresses is kind of not the same everywhere in this picture. And so to illustrate that, I'm going to draw what happens at a couple of different heights. So at t equals 1, this. And there'll be some direction that compresses. Maybe it's that direction. And so when we apply LAR inverse, this disk is going to be squished vertically. And when it's squished vertically, then we'll have a triangle that looks sort of like so. OK. And also at t equals 0, we have the same disk with the same triangle in it. But there's a compression direction which is different. So maybe down here it's this direction. So when we apply LA sub r inverse, then we will get a pancake and get squished this way. And that will affect these points differently. After squishing, the green point and the orange point will be quite close together. All right, so that's the picture that we ended with last time. Cool. And what is important here, key point, is that the compression direction is twisting relative to the unipotent orbits. Meaning that if at a given height, two unipotent orbits are being compressed towards each other, then at most other heights, they won't be. All right, so this is where we left off last time. Are there questions or comments about this picture? Yeah.
So in the picture you had last week, these after things are all kind of stretched out and compressed, and then mapped back onto the fundamental domain F. But if they've been twisted around, like, are they kind of mapped back onto F without twisting in some way to make it all perfectly line up, or is there kind of some other twisting that happens again as they get mapped back onto F?
Yeah. Okay, that's a good question. So the question is about how this gets mapped back into the fundamental domain. Let's try to draw that also. So here's our fundamental domain. First, we apply this map just in our group, and we get something which is tall and flat. And perhaps it is twisted a little bit between the bottom and the top. OK. Anyway, then that is going to get mapped back into our domain. So pi is the projection from G to G mod gamma, and which G mod gamma will identify with our fundamental domain. So this thing is going to get mapped back into the fundamental domain. What does that look like? So the fundamental domain is kind of sort of a unit cube. But this thing is way taller than a unit cube. So imagine cutting it into pieces whose height is only around 1. Okay, and this was only ever around 1. So each of those pieces now is small enough to fit in the fundamental domain. Let me call it piece 1, piece 2, piece 3, and piece 4. All right, now those are going to sort of fold back into the fundamental domain. And at least roughly, I think it's good to imagine it like this. So each one of these guys corresponds to one of those guys. Right. OK, but they are not in order. So it's not like they go 1, 2, 3, 4. They're in some order. 1, 2, 3. I don't know much about this order. I personally don't know anything about this order. OK. So now I think the question was, how would this picture look if this thing were twisted a little bit? So first of all, when we say that this thing is twisted a little bit, it's a change. It's sort of something like a change of 90 degrees or 180 degrees between the bottom and the top. And there are many steps between the bottom and the top. So that means if you just look at one of these guys, you don't notice or barely notice any twisting. This thing is basically a planar slab. And then these planar slabs are at slightly different angles. But this map pi, it doesn't exactly preserve. I mean, those angles aren't exactly well defined, because this is not living in R3. So it's actually not clear exactly what we mean when we say that this slab and this slab, are they parallel or are they twisted compared to each other? Anyway, when they get mapped back in, I think that imagining this is reasonable. OK. OK. Now that raises a bit of a question coming back to this picture that we were trying to digest last time. Like, what exactly do we mean when we say that the compression angle is twisting? Because the compression angle here lives at one height, it lives over here, and the compression angle there lives over there. And how do we compare an angle over here with an angle over here, given that this is not R3, this is living in a curved thing? Right. So I actually rethought how to state it, and I added some words that I don't think I mentioned last time. I think when we talk about this twisting, we need to include these words relative to the unipotent orbits. OK, so let me try to make a more precise statement about what this twisting means. And then we'll see how we can do some computations in the Lie group with matrices and see that it happens. All right. So, OK, so precise statement about what is twisting. What is twisting? OK. So suppose I have a piece of unipotent orbit in my fundamental domain. It starts at G naught. That's over there, some group element in our fundamental domain. And then over here, I have ut of G naught. And t goes, say, from 0 to 1. OK. Now, at each point here, there's going to be a vector that compresses when I perform AR. So let's say v compression of t. This is a vector, and this is the direction that compresses when we apply left AR inverse. Right? So it's a vector. It lives in the tangent space of our group at the given point. And it's the smallest singular vector for the derivative of this map. OK, so that's what we mean by the compression direction. Now, what does it mean relative to the unipotent orbits? So suppose that over here, I have another unipotent orbit. And this is like a nearby unipotent orbit. OK, so this might be G naught plus epsilon times V naught. Epsilon times V naught is a little vector that goes between these starting points of these two nearby unipotent orbits. And up here, or maybe here, is ut of G naught plus epsilon V naught. And here, there's a vector that goes between them, I guess epsilon times v orbit of t. So v orbit of t is going in the direction of from the red orbit to the orange orbit. OK. So the thing that is twisting is v compression of t relative to v orbit of t is twisting. The angle between those two vectors is changing. That's the precise statement of what is twisting. And we can check what it's happening by computing these two vectors. Yeah?
You're conjugating technically, right? Not just applying the left action. You're conjugating, but when you say twisting, you need to compare it at some of the same point. Right? Because if you apply the jib as a flow, then you end up somewhere else. And I'm not sure if I understand the comparison of twisting. Or are you also flowing the nearby unipotent orbit too?
Right. So the question has to do with keeping track of things given that they live in different tangent spaces. So OK, so the compression direction is a vector in the tangent space at the given point along the orbit. Is that OK so far?
Yeah.
OK. But then the comment is, if I have a family of vectors in one vector space, then I can say that they're twisted. But here I have a family of vectors in a family of vector spaces. And so it's not so clear what it means that they're twisted. So I need one way to do it is to pick a reference vector to compare them with. And so that's the job of this v orbit vector, which goes from the red vector to this, from the red orbit to this orange orbit. And that's like a reference vector. And then we'll see that so at each t, there's a orbit vector and a compression vector, and the angle between them is changing. OK. Cool. So there was a question last class that basically was like, how are we sure that this is happening, this picture? And the one way to be sure is to compute these two vectors and see that they're not the same. OK. OK, so let's compute them. Actually, one of them we can compute. So UT is a matrix. So when we can just multiply this through. This is UT G naught plus epsilon UT of V naught. And if we compare sides, we see that the orbit of T is U sub T of V. OK. Now let's figure out what V compression of T is. OK. Cool. So say we have some G naught, and we're going to apply the left action of AR inverse, and that will move us to A sub R G naught. And we want to understand how this map is distorting the geometry of G naught, the geometry near G naught. And in particular, figure out which direction is being compressed. OK. So I think the best way I could figure out to understand this is to put it in a picture with connecting this thing that I don't understand yet to some maps that are easier to understand. So here's the identity. And from here to here, I could apply a right multiplication by G naught. And right multiplication is much easier to understand because that's an isometry. And the identity also is kind of nicer than other matrices. OK. And then I'm going to go back to the identity. So this is right multiplication by AR G naught all inverse, which is also an isometry. So if you put this all together, I'm going to have a map from the tangent space of the identity to itself. And that map is an isometry times the map I want to understand times an isometry, so that all of the metric distortion is going to come from here. OK. Now, this map is not so hard to understand. So if I apply, what am I doing? So I start with some matrix H. I right multiply by G naught. Then I left multiply by AR. Then I right multiply by the inverse of AR G naught. What do I get? Well, I have H. I multiply on the right by G naught. Now I multiply on the left by AR. Now I multiply on the right by this. OK. When I invert this, I switch those. I get a G naught inverse, and they cancel. So this operation is none other than conjugating by AR. Right. So this is the conjugation by AR. OK. So conjugation by AR is a map from our Lie group to itself, takes the identity to the identity. And therefore, this map, or really its derivative, takes the tangent space of the identity to itself. All right. And now you can write this down. This AR is an explicit matrix. A tangent vector here is a matrix ABCD. So this is just ABCD goes to, or DCAR of this, is ERE minus R, A, B, C, D, E minus R, E. Right, so this is a thing you can write down. It's not that scary. And we worked out last time what it does. So recall from last time that we have, first of all, we have an orthonormal basis of TE of G, which are, there's a basis vector n, 0, 1, 0, 0. Last time I called this U, but there were so many U's on the blackboard that I was worried it was not a great idea. So I'm going to call it n for nilpotent, which is also true. There's n tilde, which is 0, 1, 0, 0. And there's a diagonal guy, which looks like this. OK. So what we figured out is that the conjugation makes n way bigger. It makes n tilde way smaller. And it leaves the diagonal fixed. OK. So if I start at the identity and I go all the way around, I'm doing this conjugation. And n tilde is the vector that's going to get compressed. But now, if I want to know what vector over here is going to get compressed, well, I start with n tilde. I map it over here. It hasn't gotten any shorter yet because this is an isometry. That's the vector that's going to be compressed in this step. OK. So it's the right action by G naught of n tilde. This is the singular vector of dLAR inverse with singular value e to the minus 2r. OK, so that's basically the answer to our question. So the the compression vector at t, that's r at, so now I'm not necessarily at the point g naught, but I'm at the point ut g naught. So it's right by ut g naught of n tilde. So that's n tilde ut g. OK, so now if you compare how these two things are changing with t, you see it is not the same because our group is not commutative. Because when you're changing the orbit of t, you're multiplying by ut on the left. But when you're changing the compression direction, you're multiplying by ut over here in the middle. And it's a non-commutative group, so those two operations are not the same as each other. So I don't necessarily think it will be helpful to do more computations, but I did some at home to be sure. And if you imagined that at time 0, these two directions coincided, and then you see what happens as t changes, you'll see that they stop coinciding. Yeah?
Let's say taking the inner product of the vectors, it makes sense as an operation to do to compare the angles in the tangent space?
Yeah, that's right. So these are vectors in a Riemannian manifold. And so they have a well-defined angle, and we can compute it by taking inner products. And then, right. So I guess we could say that the cosine of the angle between v of t and w of t would be v dot w over norm of v norm of w. I used to teach this a lot in 1802. I think that's right. So we have formulas for v and w, so we can compute this. And it'll be a little messy, but we'll see that it is not constant in t. Okay. Other questions or comments? OK. So the first big goal, that was the first chunk of the class. The first big goal of the class was to check that this picture happens. And then the second part of the class, we will discuss how to use this picture to figure out stuff about a long unipotent orbit. OK, so let's switch gears. OK. OK, so let's call this tracking the spread of an orbit. All right. So remember that we had this u0t of x is AR u01 AR inverse x. Let's call this guy x tilde. OK. Now this, there was a discussion last time. What happens if this orbit here is periodic? If this orbit here is periodic, the special thing that happens is that this point x tilde will be deep in the cusp. And the deep in the cusp is sort of a special case, because we were imagining that this was like a regular nice orbit of length 1. But if it's deep in the cusp, it's sort of different. So let's assume that x tilde is not deep in the cusp. And that's equivalent to saying that ux is not close to periodic. OK. And let's break up r as capital J times little r. And so then I'm going to say that uj is a little r to the j of u01 of x tilde. OK. And I want to track how this thing is spreading out through my homogeneous space, G mod gamma. And we're going to track it by noticing how many delta balls it takes to cover it. So recall that x delta is the minimum number of delta balls needed to cover x. And so our goal is going to be to estimate uj delta in terms of j, delta, and r. OK. And for context, for reference, we have a three-dimensional space. So for the whole space, the number of delta balls that we need to cover it is delta to the minus 3. OK. Cool. All right, so next of all, our uj is like a bunch of these unipotent orbits. Looks like that. And so you might notice that it only really matters what the top cross-section looks like. All the other cross-sections are similar. So let's take that top part down. Inside of there, we see this. So let's call that xj. That's the top cross-section of uj. And then it's not hard to check that uj delta is like delta inverse times xj delta. I have cut it into slabs of thickness delta. For each thickness, the number of delta balls that we need to cover that slab is xj delta, and this is the number of slabs. OK, so So basically, we want to track how xj delta depends on delta. So fully spread, or maybe I'll say very spread. That means that uj delta is like delta to the minus 3. And that would be like saying xj delta is like delta to the minus 2. That xj really fills a lot of the disk. OK. So now, how does this picture help us to study xj delta? So using the key picture. All right. So let me label these maps pi 1 and pi 0, and somewhere in the middle we would have pi t. Pi t is what our map AR is doing to the slice at height t. OK. Using the key picture, have a lemma. So if e to the minus 2r is delta, then xj plus 1 delta is around a sum over t of pi t of xj delta. And which t's do we sum over? The t's are in delta z, and t goes from 0 to 1. This is all. We can also write this as delta inverse times the average t between 0 and 1 of pi t of xj delta. OK, so proof sketch. OK. So here is our fundamental domain. Cut it into slices of thickness delta. So here's a slice at height t with thickness delta. OK, now when we apply LAR, we stretch it up vertically, and we compress it in some other direction. We get something like this. And then we divide this into pieces at different heights. And let me color this particular slab in red. So that red one is one of them over here. So these are each of height 1. OK. Right. Right. So in this new picture, there will be, so in the old picture, there were some unipotent orbits that went through our slab. So x describes where the unipotent orbits hit the top of our slab. And now we apply this map, and now there will be some points over here in the top of this slab. And who will they be? Those points over there would be pi t of x. OK, now we want to cover things with delta balls. So this distance here is e to the minus 2r. So that's delta. So we want to know how many delta balls does it take to cover that. So that number there is delta covering number of pi t of xj. So over here, we started with xj. Now, what happens when we apply pi? Each of these slabs gets folded back in. Okay. The red one went somewhere. I don't really know where, but maybe it went over here. And here in the top of it is pi t of xj, and its delta covering number. So the number of delta balls in this strip, that would be pi t of xj. OK. And now these dots up here are xj plus 1. It's the set of dots on the top face. And so how many delta balls do we need to cover them? Well, for these ones, we needed pi t xj delta covering number. And these other guys, those corresponded to different slabs here. So there are different terms in this sum. OK. So now we can try to use projection theory to study this thing. And it will tell us how the covering number xj plus 1 delta evolves as we increase j. Any question? Yeah.
Why do when you get delta balls start to overlap when j is large enough and kind of the compression is more than delta? Because delta is kind of the size of one round of compression. If you do multiple, why would it overlap?
So I think the question is, suppose at the beginning that there happened to be two guys here in x whose distance was less than delta, which might happen. Yeah. Then what would happen to them? Well,
not that they're less than delta, it'd be slightly more than delta, but less than e to the minus 2r, or e to the 2r delta. So that in f, they're in the same delta ball. Then applying the transformation, diagonal transformation, then they become in a delta ball. Before they're in two separate delta balls, after the transformation, they're one delta ball.
Right. OK, so it could happen that we have two guys, like maybe these two guys are pretty far apart, but after we perform pi t, they got squished together, and they're now in the same delta ball over here. Yeah, that could happen. And the main thing we have to study is how often that happens. But this lemma is still true. This might be a lot smaller than xj delta, because many points that were far apart in xj may have gotten squished together in pi t of xj. But this is just the number of delta balls that it takes to cover the image there. Does that answer your question?
Yeah, I guess also, like, in the third image, like, why is kind of each delta ball contained in only the size of one of those kind of strips?
OK. So we tuned delta and r to play together, so that we picked r, so that the thickness of this strip is delta.
I thought if the transformation is applied multiple times, then you get multiple, like either the -2 or j scaling.
That's not wrong, but when we apply it multiple times, we're not changing little r. We're just applying a sub little r multiple times. So this picture is describing what happens in one time. And then you could use this in many rounds. So you could use this lemma over and over again, which is what we'll do. OK. Let me change my notation a little bit. So I was using the letter pi for this, maybe a little bit prematurely. What's clear so far is that this is a map. So I'm going to call it f1, ft, and f0. And so then I'll change this. OK. OK, so now the next remark is that these maps look a lot like linear projections. So remark, ft is kind of approximately an orthogonal projection pi t. So let me make a picture. So ft does something like this. And this thickness is delta. This is 1. And then pi t would just be an actual orthogonal projection. OK. So ft is not perfectly linear, but it is smooth. OK. So now here is a proposition or exercise about projections. It says that if x is in the unit ball in the plane, then if you take the average over all directions, theta in S1, of pi theta of x delta, that is at least as big as x delta to the 1/2. Here's an example that shows where the x delta to the 1/2 comes from. So here's the unit ball. And then inside of it, I take a smaller ball, and I call that x. So x is the ball of some small radius rho inside of the ball of radius 1. OK. Then when I perform an orthogonal projection, here's pi theta of x. In any direction, I'll get a line of length rho. So I see that x delta is like rho over delta squared. And pi theta of x, delta covering number, is like rho over delta. So this is the square root of that. OK. And this is the best thing to do. You could devise an example where in one particular direction, the compression is much smaller than the square root. Here's an example like that. V1. Here's x. Here's theta. OK, in this example, pi theta of x delta is much smaller. I'll call this theta naught, much smaller than x delta to the 1/2 for 1 theta naught. But at least in this picture, most of the projections are way bigger. OK, so it's not super difficult to check this proposition. And I'm going to make it an exercise. I think we're out of problem sets. But if we weren't, this is a nice one to review the class. OK, and another comment is, even though these FTs are not exactly linear maps, so that we cannot just literally apply this proposition, they're close enough that by using the proof of this, you can get it for FT2. So remark, the proof applies to Ft also. OK. So if we put together this lemma and this proposition, we'll get an estimate about the delta covering number of xj. OK, so corollary, if we put these together, xj plus 1 delta covering number is at least around delta inverse times xj delta to the 1/2. Proof. So xj plus 1 delta is at least, by our lemma, delta inverse times the average over t of xj of ft of xj delta. And then by our proposition, that's at least delta inverse times xj delta to the 1/2. And that's the proof. OK, so then let's just track what this means. So x0 delta would be 1. Think about what x0 delta means. It's one unipotent orbit. OK. So therefore, x1 delta would be at least around delta inverse. x2 delta would be at least around delta to the minus 3/2. x3 delta be at least around delta to the minus 1 3/4. And so on. And you'd get pretty close to delta to the minus 2. OK, and delta to the minus 2 would be like a definite fraction of the whole space. All right. So this proves that a unipotent orbit that's not close to periodic, it proves that it fills up a lot of the homogeneous space. It's not Hedlund's theorem. Hold on a second. So we didn't prove yet that the orbit is dense. The orbit could be missing an entire ball that's like half the size of the space, and this could still be true. But we did prove that the orbit goes a lot of places. Yeah?
In this proof, since applying it each time loses some sort of implicit constant, how do we know that it's not becoming dense and just kind of an infinitesimally small region of this whole space?
Right. So I think the question is, we didn't actually get to a constant times delta to the minus 2. And if I tried to do this sort of infinitely many times, I would be losing a constant each time. Yeah, that's right. So imagine doing this 10 times, and we get delta to the minus 1.99. And that's what the method proves so far. So stronger things are true, but this method doesn't prove them yet. So remark, this doesn't show that the orbit is actually dense. And so maybe a question, could the orbit do this? So here's our homogeneous space. There's a cuts, but it's not that important. And then the orbit goes around a good bit, but it only ever goes around over here, and it never goes over there. So this proof doesn't say anything about that. No. OK. So as far as I know, to finish Hedlund's theorem requires another step that is based on different ideas from these ideas. So there's more to homogeneous dynamics than this story. But we did still learn something interesting. Cool. Yeah.
Do you know how close it's possible to get to the full theorem by trying to optimize all the constants in this proof?
OK, so there are two things that we might like to improve here. So the question is, how close can we get to the full theorem by optimizing the argument that we've been talking about. So one thing that you might like is you might like to actually get to delta to the minus 2. That still wouldn't necessarily rule out this possibility, but it would be interesting. And if you look at this proposition, one thing that you sort of notice that this proposition is sharp in this very clumped case. And if you remember back to the early months of our class, if x was not so compressed, then there would be even better estimates. So if you knew as an input that x is not too clustered, then you could get all the way to delta to the minus 2 in one step, or 2 steps or something. And so you might try to track that. You might try to track not just the delta covering number, but also the rho covering number for different delta and rho. And then you could take advantage of this clustering. And I am not positive, but I think it is a reasonable 18156 project to try to use that to get all the way to delta to the minus 2. Okay. Even if you got a constant times delta to the minus 2, it would still not be obvious to me that you filled the entire manifold and that you're not missing a ball. And I thought about it yesterday and today, and I don't have a good understanding yet of what you need to get everywhere. So I would be interested to learn if people have thoughts about it or know about it. OK. Cool. So I think that there actually are a bunch of ways to prove Hedlund's theorem. And this is not one that I have seen in the literature. And all of these problems become more difficult and maybe more interesting when you go to higher dimensions. So the projection theory also becomes more difficult and more interesting in higher dimensions. And I wanted, in the last part of the class, to just show you what happens. And in particular, we will see a new question about projection theory that we haven't mentioned so far in this class, but which I think is a really cool question. OK. OK. So I'm going to put it this way. What about SLNR? Right. OK. So I'm going to take a somewhat specific example, although I think most of what we'll say then would work for any n. So for example, we could have SL3R for our G. Gamma could be SL3Z. And U could be the unipotent group of matrices that look like this. So from what I understand, there are several different one-parameter unipotent subgroups of SL3R. They're slightly different from each other. And this one is sort of particularly well studied in the homogeneous dynamics community because it's the one that comes up in the Oppenheim conjecture about quadratic forms. OK, but anyway, so we have this one-parameter subgroup. And so let's call this U sub t. OK, so our basic setup with like conjugating by a diagonal matrix, that works. And the relevant diagonal matrix is this matrix. OK, and then you can check that A sub r, U sub t, A sub r inverse is U sub e to the rt. Turns out to be e to the rt, not e to the 2rt, but that's not too big a deal. OK. So now we have a bunch of unipotent orbits like before. There's a bunch of unipotent orbits. But the dimension of our group is 8 instead of 3. And so we have the direction along the orbits, t equals 0 up to t equals 1. That's still one-dimensional. So this thing here is a 7-dimensional ball instead of a disk. OK, so now we apply, we study the action of LAR inverse. And we'll have a picture like this. F1, F0. And OK, something here will happen, and something different here will happen. OK, so you can study the singular values. The singular values of LAR inverse. And those are equal to the singular values of conjugation by AR. So conjugation by AR is a very nice operation on matrices. You can write it down and see what happens. And you can compute these singular values. And they are as follows. E to the minus 2r, e to the minus r, e to the minus r, 1, 1, e to the r, e to the r, e to the 2r. I won't do it on the board, but I promise it's not hard. OK, now one of these singular values corresponds to the u direction. So little n is the vector that's the tangent vector to the group u at the identity. And so little n is, it's not super important what the formula is, but if you differentiate that, you'll see that the tangent vector is that. And that's one of these guys. So as before, the direction of the orbits is expanding. And then on the B7, we have the other 7 directions. So this thing over here is an ellipsoid with axes e to the minus 2r, e to the minus r, e to the minus r, 1, 1, e to the r, e to the 2r. OK. So as we go from here to here, these f's are not exactly linear, but they're close to linear. They're close to linear maps. And they stretch some directions, and they compress other directions by these amounts. OK. So what is different from before? OK, one difference is that this thing is not exactly a projection. But that's not the most important difference. So differences from last time. Right. So if we had like an approximate projection that went from the 7 ball to some vector space V of dimension 3, say, so 4 dimensions are getting squished and 3 dimensions are staying as they are, that would sort of be approximately a linear map with singular values e to the minus r, 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 1, 1, 1. Right, if I had a linear map like that, these guys are almost 0. So these are the 4 directions that are being squished. These are the 3 directions that are staying the same. The list of singular values here is not quite like that. Some of them are bigger than 1. We didn't have that before. And the ones that are, some of them are equal to 1. The ones that are smaller than 1 have 2 different scales. So that's a little bit more complicated. But I don't want to focus on it. So our singular values are a little more complicated. OK, let's ignore that. Suppose each of these linear maps actually had those singular values. So it was more like what we were used to in projection theory. There would be another difference from before, which is more important. So number 1. Number 2, we still have only a one-parameter family of linear maps. All right. So before, when we talked about projections from B7 to V to three-dimensional vector space, we talked about like all of them. If you look at all of the projections from B7 to three-dimensional vector spaces, then something nice happens most of the time. But we don't have all of them. We just have a very thin subfamily. So this is not all of the projections. Cool. OK. So there's also a cosmetic complication that 7 is a lot of dimensions and there are a lot of numbers. But that's not that important. It's just a pain. But these are this to some extent, and this is a really fundamental conceptual difference. So I wanted to show you not this problem, but the simplest problem of this type, which is called the restricted projection problem. All right, so this question, which I think is a cool question, was raised by Fassler, Katrine Fassler, and Thomas Orpinen in 2013. And the question is like this. So here's the two-sphere. So we're going to be doing projection theory in 3 dimensions, in R3. So the different directions are parameterized by the two-sphere. But we're not going to project in all of them. We're just going to pick some curve gamma and project in the directions of gamma. So gamma contained in S2 is a curve. OK. The question is like this. If x is contained in the unit 3 ball, and let's say x is a delta SC set, to make it interesting, we put some kind of non-concentration condition. And this is the one that they had in their paper, basically. OK. Then estimate the average over all the directions in gamma of pi theta of x delta covering number. OK, so theta is a direction, an element of S2, and pi theta is the orthogonal projection from R3 to theta perp, so from 3 dimensions to 2 dimensions. Okay. So estimate the average of that. So I still have, I erased the wrong thing. OK, on this very board, not 2 minutes ago, there was a proposition that said if you had a set in R2 and you projected it in all the different angles, then on average, the delta covering number of the projection was at least something or another. So this is like an analog of that in 3 dimensions for a set with a spacing condition, but with the key difference that we're not averaging over all of them. We're only averaging over the ones in a particular curve, gamma. OK. Now, an interesting thing about this question is that it matters what the curve gamma is. And in particular, there's a big difference between an equator, which is sort of like a straight line on the sphere, and a non-degenerate or curved gamma. So the answer depends on whether gamma is the equator is one extreme, or gamma non-degenerate is another extreme. Instead of writing the definition of non-degenerate, let me just give you one example of a non-degenerate curve. So an example of a non-degenerate curve is gamma is equal to the set of theta in S2, so that the third component of theta is a half. So it looks like the boundary of a spherical cap. OK, so let me show you how these are different from each other. OK, so example. Say gamma is the equator, and S is 2. So we have a sort of a quote-unquote two-dimensional set, a delta 2 set. OK, so our set X is going to be a delta by 1 slab. So that looks OK. And so imagine that the two big directions are in the plane of the blackboard, and this slab is sticking out of the blackboard by a little bit delta. OK, now there's an equator of directions that we're going to project in. And think of that as the equator that's like the sphere was centered at the blackboard. You intersected the sphere with the blackboard, you would get a circle. So here's gamma. So now if theta is in gamma, then the projection of X is a delta by 1 rectangle. And so there's a circle of directions where if you project this slab, you just get a delta by 1 rectangle. OK, so then we see that the average pi theta of X delta is like delta inverse. OK. OK. Now, there's no obvious version of this example where gamma is that curve that's up nearer the top. And the difference is, so if you're projecting in a certain direction, then the fibers are like lines in that direction. And so what's special here is that all of these lines are coplanar. And so you could have a kind of planar object that has a lot, where these lines intersected a lot. And instead, when we have those directions, then all of our lines make an angle of 45 degrees with the horizontal. They're like light cones. And these just don't fit together in the same nice way that coplanar lines fit together. So it makes a difference. And Fassler and Orpinen, they proved that it makes a difference. So they proved some bounds for that thing that are strictly bigger than this thing. But it took a while to figure out what is the sharpest bound. And that was figured out sometime later in a paper of 6 authors, Shengwen Gan, Xiaoming Guo, me, Terence Harris, Dominique Muldog, and Han Wang, many of whom were here working on it at various times. OK, and we proved, I'll just do a special case. So if X in B3 is a delta 2C set, and gamma is non-degenerate, like this example above, then the average theta in gamma of pi theta of X delta covering number is bigger than C epsilon delta to the negative 2 plus epsilon. OK, and the best thing you could hope for here is delta to the minus 2, because X itself probably has delta covering number delta to the minus 2. So up to small issues, that this is the sharp theorem. OK. This proof is based on some version of the Fourier analysis method, but it's a more difficult version that involves decoupling. OK. Cool. So this connection between projection theory and between homogeneous dynamics and projection theory was discovered by Ilan Lindenstrauss and Amir Mohammadi, who were working on quantitative estimates for how unipotent orbits become dense in this setup. And they realized this connection with projection theory. And they found the literature. They found the paper by Fassler and Orpinen and all the follow-up papers. And they used those tools to prove quantitative estimates about how these unipotent orbits mix. Yeah?
Isn't the question in projection theory where kind of each unipotent element kind of reduces a different projection is that set of projections dense in kind of the whole space of projections, or is it some non-dense subset?
No, it's some non-dense subset. Yeah, so here, t is going from 0 to 1. For each t, we have more or less a projection. And so we have a smooth curve of length 1 in the space of not exactly projections, but the space of linear maps. And so it is not in any sense becoming dense in the space of linear maps. It's really just a few special ones. And this is a reasonable model to picture in your mind. Like that sphere is like all of the projections or all of the linear maps. And that orange circle is the ones that come up in homogeneous dynamics. Yeah. OK. So in the last 2 minutes, I will write down a theorem that they proved. At least approximately. OK, so this is Lindenstrauss-Mohammadi, Wang, and Yang. So setup is on that board. So if G is SL3R, gamma is SL3Z, U as above. OK, we take X, and we suppose U dot X is not close to a proper homogeneous subspace. So this is some analog of being not close to periodic. OK, then the conclusion is that U0T of X is delta dense in the homogeneous space. But so the homogeneous space has infinite diameter, so this can't quite be true. But if you cut off the cusp, so you cut off the cusp, so you have a compact piece of this. And delta is t to the minus c. C greater than 0 is a universal constant. OK, and a key step in the proof is to first show an estimate of the kind that we were talking about, that the delta covering number of this orbit is pretty big. So the biggest it could possibly be would be delta to minus the dimension of the group. That's the delta covering number of the whole space. And it's quite close to that. That's a key step. It's analogous to the proof that we sketched for the simpler SL2R case. And there is an additional argument, but it seems like the most novel and important part of this paper was using projection theory, using those kind of theorems, plus some other smart stuff to show that the orbit covers a lot of ground. OK. OK, so homogeneous dynamics is a big subject, and there are different techniques. But in this course, I wanted to show that there's a connection to projection theory, which is one set of techniques, and which helps to say some interesting things.